Welcome back, Professor Bright here, and we are going to start a new section of the course. So we have been studying trigonometry up until this point, and then also looking at different applications, including vectors, where we had to use, cosine theta, sine theta for the x and y components. So we're done for trigonometry-ish. There is a way that trigonometry does flow into what we're going to be doing next, but we won't see it until much later. We need a little bit more practice with the basic skills with systems of equations, so that's what we're going to look at next. So we're going to build in this, and then we'll link trig and systems of equations, well, actually matrices, together later on. So if you would like to go back to trig, you certainly can on your own, but we're going to press forward. Okay. When we look at systems of linear equations, you might remember what a linear equation is, like y equals mx plus b, and this was probably hammered into your head back in school. Now we're going to focus on the general form. So I have the three forms of an equation of a line and two variables at the top of the screen here, so or middle of the screen now, I should say. And so we're going to use general form usually, but what we're going to see is that we are given multiple lines. Okay, all in one system, so it has a little bracket at the end, so it'll be like this, and then it'll be like equation 1, equation 2, and that we call a system, and it just is a connected equations that we have to simultaneously satisfy. And we're going to try and find the solution just where or try and find that x and y value that satisfies both conditions simultaneously. Okay, now you might remember that, okay, we have linear equations, we have lines, right? So we should be able to graph them, okay? And so we're going to graph a system here as practice and see if we can find that x and y value that satisfy the system. When we find that x and y value, we call that the solution set, just a set of x and y that make the equations true. Okay, or that satisfy them. Okay, so for each of these, when we graph them, you might want to change them into a different form. So, for example, this first one, you may want to, move the y to the right side, move the 10 to the other. So this is y is equal to 3x minus 10. And then similarly, if you manipulate this around, isolate y, because again that's what we're used to and that's perfectly okay, you would get y is equal to minus 4x plus 4. Okay, so then we go down 10 units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then that's our intercept, and we go up 3 into the right one, so 1, 2, 3, 1, 1, 2, 3, 1, 1, 2, 3, 1, okay, and then similarly for the other one we do 4 as the y-intercept, and then from there we go down 4, 1, 2, 3, 4 over 1, down 4, 1, 2, 3, 4 over 1. And so our first equation, if I graph this in red, would be something like this, and our second equation, if I graph that in green, is going to look something like this. Okay, and graphically, I think I found their point of intersection, which appears to be when x is 2 and y is minus 4. Okay, so then I would say, I maybe want to get a better sketch just to confirm, but I would say the solution set is, and then it is the point 2, negative 4, but since we are saying a set, we have to include it in set brackets, those curly brackets. Okay, so whenever we're asking to state the solution set, it's stated in this form. Okay, and certainly to get a better picture, if you want to, you can certainly hop into Desmos and get a picture there. And so here in Desmos, you can see I've graphed, and this in red and blue, but I've graphed the two equations, the first one in red, the second one in blue, and if I look down here, I can identify that if I just kind of click on that point where they meet, it does identify it as x is 2 and negative 4. So that is the solution set for the system. It is the x and y value that simultaneously satisfy these two lines. Okay, so then going back here, all we want to do when we're trying to find a solution set for a system of equations is find the point of intersection. But do any pair of lines necessarily have a point of intersection? And if they don't, what are the other options? So here I encourage you to go to Desmos, okay, DESMOS.com. And then there's a calculator there that you can use. Graph these sets of each system at one at a time in Desmos and see what you get. If you graph the first set, you'll notice that the first system is in green and purple here, and if you look at them, they're parallel lines. Okay, so then we're thinking, what is the solution set for this? Okay, well, okay, I had to have a point of intersection. Parallel lines never intersect, so what is the solution set here? We would call this system inconsistent, and I'll write it down here in a minute. But when we have parallel lines, at least graphically, we would say that the system is inconsistent. Okay. For the second system, if you graph those, you'll notice that, okay, let me just see that I did that correctly. Yep, it's all put in there correctly. But then when I turn off the orange function, or the orange graph, it seems like the black and the orange lie on top of one another, and that is correct. So when this happens, we have that the lines would intersect at infinitely many points. Okay, and this, we would say that the system is, so there would be infinitely many solutions, and the system is dependent. That's the language that we would use when we have two lines as the same line. Okay, so let's capture those results on our notes. The first system, we said these were parallel lines. And so there's no intersection point. And then the language that we use here is that the system, we have an inconsistent system. For the second system, we said, okay, these intersected at, so these are the same line. And here we had infinitely many solutions consequently. And when we have this, we would call this system dependent. Okay, we'll dig into these a little bit more once we get into the algebraic approaches, but for now, inconsistent system goes with parallel lines. Same line means that you have a dependent system, and that's what we captured here. So when we have one unique solution, the solution set, we can just do squiggly brackets AB, that's fine. When we have an inconsistent system, that means that they don't intersect at all. So we would actually say there's no solution. Okay, so inconsistent systems have no solution. And then the last thing, when we have a dependent solution, we actually have infinitely many solutions, and we can write that as a solution set. This is just an example. We will see that in coming videos, how to write that out. But for right now, we just have to identify it as dependent. Okay, so later videos we're going to, instead of looking at graphical approaches, we're going to look at algebraic approaches, so stay tuned for those.